Hello everyone. Okay, this is a remake video for the example 10.5. Okay, the reason for me to remake this video is I want to unify the sign convention in torsional load problem. Okay, so let's look at the example 10.5. This problem is a angle twist calculation problem. It said that the rod is there's we apply this rod. We apply multiple torque on this rod or on this shaft, and he want to calculate. Okay, what's the angle of twist of A relative to C? Okay, and for this problem, I think I also ask another question is okay. What is the angle of twist of A relative to D? Okay, let's say phi A relative to D and phi A related to C. Okay, and for the angle of twist problem, what formula we should use? Okay, we should use the formula called TL over JG. Okay, what is T? T is the torque, L is the length, and J is the polar moment of inertia, and G is shear modulus. And in this problem, what is the shear modulus? This problem only tell you this A36 steel. Okay, but when you look up the table at the end of the textbook, it will give you the shear modulus for the A36 steel is okay. This value is 7.75 gigapascal. Okay, and for the this angle twist problem, we also need the polar moment of inertia J. Okay, and then J we need J is equal to pi over 32 d. Maybe I should use small d to the power 4. Okay, and what's the diameter for this cross section area? It says the diameter is 200 millimeters. Okay, so okay, that's right now. Let's first to calculate what's the J. Okay, let's summarize the information. We have 20 millimeters. So 200 millimeters. Sorry, 200 millimeter into the power 4. Don't forget it's per power 4. So what's the value? Its value is 1.5710 to the power minus 4, and its unit is m to the power 4. Okay, so let's back to this problem. Okay, when we apply a multiple load on this shaft, actually this load will create angle of twist inside the shaft. Okay, and for this in this course, every material is very hard. Okay, so the torsion only causes the deformation of the local area. It causes the deformation of local area. For example, for this problem, we can also use the section method. Okay, we can cut the section here, and section here. In this section, we have torque AB, and this section we have torque BC, and this section we have the torque CD. Okay, and the torque AB will cause the local deformation of AB section, and the torque BC will cause the deformation on the BC section, and the torque CD will cause the deformation on the CD section. So, and then if we want to know what's the angle of twist with respect to, for example, if A with respect to D, just add all the deformation, or add all deformation together. Okay, just like we add a phi AB plus phi BC plus phi CD equal to phi AD. Okay, because each torque in each section, the torque in this section only causes local deformation of the section. So the deformation in AB won't affect the deformation in the BC, and the deformation of BC won't affect deformation on AB and CD. Okay, so the same thing, the low deformation on CD won't affect the deformation in BC. Okay, so you can see it's independent to each other, like linear combination. Okay, so let's also write it down. Okay, if we want to calculate phi AD, actually we just call phi A related to B plus phi B related to C plus phi C related to D. Okay, so how to calculate angle of twist in this three section? Okay, just like we use a cross section method. Okay, so in the cross section method, after you use the cross section method, you have to make use the rigid body equilibrium to calculate the local torque, such as the TAB, TBC, and TCD. Okay, so let me write the local this cross section. Okay, the cross section is here. Okay, just wait for me. Uh, here, and here is A. Here's A. It's called A is 80. A is called 80, and here is A. Yeah, wait for me. A B B B B B B B B B B. Torque. So I need to know its direction. See, here is 10. 10, 60. Oh? Sorry, what's the value? 80. Okay, 150. 150. Sorry, this should be. This should be. This should be 60. Sorry. Okay. Take a while to finish the cut section picture. Okay. Okay, so let's do the cut section method. We cut in AB section, in middle of AB section, middle of BC section, middle of CD section. Okay, so let's look at the first one. Okay. Okay, here we will have in the cut section, in the first step, we will have a torque AB. Okay, and the torque AB, I should assume the torque AB, which direction? This direction? Torque AB. Okay, so here we also use a sign convention. Okay, using your right hand rule. Okay, so if torque AB rotate in this direction, where is the thumb direction? The thumb direction is point outward to the surface. So that's positive. Okay, I keep saying this. Okay, if your thumb direction is outward to the surface, that's a positive. Your thumb direction is inward to the surface, that's a negative. Okay, so we assume TAB is rotate in this way, so it's outward to the surface. Okay, same thing. We also assume the TBC rotate in this direction, and also the TCD rotate in this direction, or it's all point out to the surface. Point out to the surface. Okay, so that's first thing. Okay, then it's called sign convention of torsional load. Okay, and next thing we want to do is, okay, let's do the rigid body equilibrium of each set. Okay, each set. Okay, I should call it, this is the first set, second set, third set. Okay, so, okay, let's say for the first set, okay, rigid body equilibrium, okay, summation torque must be equal to 0. Okay, so here is a torque A. The value of torque A is 80 kilonewton times meter. Okay, it's 80. Okay, it rotates in this way. Okay, it's rotating this way, so its thumb direction. Okay, use your right hand. Okay, it's rotating in this way. It's rotating in this way, and use your right hand rule. The thumb direction is point outward to the surface. Point inward to the surface. Point inward to the surface, because right now our surface is here. Okay, the torque A, use the right hand rule. Okay, its thumb direction is inward to the surface. Okay, so the AT here, its sign is minus 80 because it's inward to the surface, and plus TAB is equal to 0. So you will have TAB is equal to 80, and don't forget the unit, kilonewton times meter. And for section 2, okay, the torque A we already know is negative. What about torque B in section in the second set? Okay, also use the right hand rule. Its right hand rule is rotating in this way, so your thumb direction is here. Okay, and this direction is outward to the surface. Okay, this direction is outward to the surface. So this is minus 80 and plus 150 and plus TBC is equal to 0. So you will have TBC is equal to, what's the value of it? It's minus 70 kilonewton times meter. Okay. So, okay, let's see the section 3. Okay, the torque A we know is negative, torque B positive. What about torque C? Torque C use the right hand rule. It rotates in this direction. That is, some direction will be here. Okay, use your right hand rule. Okay, this direction is inward to the surface. So the torque C is negative. Okay, so the torque A is negative, torque B is positive, torque C is negative, sorry, minus 60, and plus TCD equal to 0. So you have TCD is equal to, what's the value? I think you should check yourself. The TCD is minus 10 kilonewton times meter. Okay, so after using cross section method, we obtain a TAB and TBC and TCD, and finally, and I think we get all the information we get all the information we need. Okay, so what is phi AB? Okay, phi AB. Phi AB. What is phi AB? Okay, the deformation of the local area between AB. Okay, it's torque. What is torque? It's torque is TAB. Okay, TAB is 80, and don't forget we have kilo here, so it's 80. Maybe I should use a color. Okay, so what is phi AB is equal to 80. Don't forget we have kilo here, so 10 to the power 3. Don't forget T. Okay, L. What is L for the AB section? But L for AB section here is 3. It's 3 over J. What is J? J is here because the cross-section area are the same. The cross-section area is polar moment of inertia. Polar moment of inertia 1.57 times 10 to the power minus 4. Okay, and what is the G is shear modulus is 75 gigapascal, so 10 to the power 9 gigapascal. Okay, so I leave the equation here. Okay, I also draw. Okay, so it's very easy. So what is 5 BC? Okay, you just apply your torque. Your torque is minus 70, 10 to the power 3, and times 2, and numerator and denominator is the same, 10 to the power 9. Okay, that's by BC. What about the phi CD or phi CD? I don't have any space here. Okay, so right here, phi CD is equal to, what's the torque? Torque CD is 10 minus 10 to the power minus 3. And what's the length in this CD section? It's 1.5. Okay, and the J, same polar moment of inertia, the same. And the G is 75 10 to the power 9. Okay, so we have all the information, so we can calculate the value. Okay, so I just give you the value is okay, if you add these three together, the value will be let me see, is 7.212 times 10 to the power minus 3 radian. Okay, that's the first answer. So if you want to calculate the A relative to C, let's just add these two together. Okay, add these two together. Okay, and what's the value? I think give you the answer is 8.482 times 10 to the power minus 3 radian. Okay, radian. Okay. Okay, so here's a remake video for the example 10.5 in the torsional loading. Okay, yeah, I hope this can fix the sign convention issue, because in the previous video, in the previous version video, the answer I get, it has a negative sign. Okay, because there was sign convention issue in the previous video, so I want to remake the video to fix the issue. Okay, so I'll stop the video here. See you in the other video. Bye bye.